this is a radical departure in topic from what you've seen before, because I'm not a member of LIGO. I am a physicist. I do my science at the Large Hadron Collider in Geneva, Switzerland, so I'm an experimental particle physicist. But I'm also the director of the San Diego Supercomputer Center, and I'm the executive director of the Open Science Grid. And so I'm on the LIGO or Physics Advisory Committee. So I sort of look at LIGO from the outside in, and what I'm talking about is what infrastructure LIGO uses, as well as a host of others, in order to do global science, share data, and how you can join this and participate and get access to that data. So I'm going to talk about 3 topics: the status of the infrastructure as it stands today, how an institution or an individual can join, and where this infrastructure is heading. So the status today in a nutshell is that there's 2 organizations, OSG and PRP. PRP stands for Pacific Research Platform, that operate open infrastructures that any researcher affiliated with any US science program can join their resources to, and these 2 infrastructures interoperate. That means that every single one person in this room can get an account and access the public data of LIGO and play with it. But it also means that your group, your lab, your institution can join its hardware resources, its cluster, individual hardware, and so forth to that infrastructure, and therefore contribute and host data, add data, and so forth. And I'll talk about what I mean by this. And the 2 buzzwords that go with this is that we're operating a compute federation and we're operating a data federation. And in a nutshell, you can think of it, the computers inside the compute federation access the data in the data federation via a bunch of APIs and so forth. And I'll talk a little bit of how this all hangs together. I'll be fairly techno-free as much as I can help it, in order to just communicate the concepts and principles. So what do I mean by federation first? Federation means distributed control. The owner of a resource determines who gets to use it, and that implies that policies are always set locally. And then the resource consumer determines the policy of what they're willing to use. So LIGO decides as a resource user, I'm willing to use resources of the following kind, and then as an institution, I can join my resources and offer my resources up. And then these projects like OSG and PRP, they provide the necessary services in order to match consumers to providers, and voila, science gets done. That's basically the principle. A simple example, if I own a compute cluster, I may want to give 20% of my compute time to IceCube, 35% to LIGO, 25% to CMS, and 20% to anybody who's running around in the national science and engineering community, and is accredited with some institution. And as a researcher, I may want my application to run on a host that has following characteristics. It has 8 x86 cores. It has a certain amount of RAM, a certain amount of disk space, and then it has access to the LIGO runtime environment and the LIGO data. So I can specify this is what I want as a user. As an owner, I can specify these are the people who are allowed to run, and my organization makes these 2 requirements meet, and voila, everybody's happy. That's how this works in principle. So now this here is a picture, obviously, of the Earth, a map of the Earth. And the green points are compute clusters worldwide. I believe that there's 136 dots on this picture. And so there is more than 100 clusters worldwide registered directly with OSG. In addition, there's another couple hundred, maybe even 300, that OSG federates with via other partners. And so in totality, you can reach from an access point, meaning from a login, an account that we can give you, you can reach in the neighborhood of a few hundred clusters worldwide. Then how does the data get there? We've built something I like to call a content delivery network. That is techno speak for we built a network of caches that automatically pull the data where the computing wants it to be. So there's 18 caches across 4 continents. LIGO is in fact the primary driver who made this happen. The fact that it's global is to a large extent because LIGO, Virgo, Kagra are global. For example, this here is in Korea, if I remember correctly. They are a Kagra supporter. I believe if this is another LIGO site, the only origin, meaning we distinguish origins where the data is and caches where the data gets accessed from by a computing job in their vicinity. And there is one cache outside the US, and that is to host the Virgo data. So in essence, the Virgo data comes from here. The LIGO data comes from Nebraska for odd historical reasons. The private LIGO data comes from Nebraska, whereas the public LIGO data comes from Caltech, strangely enough. All historic accidents to a large degree. And things like that. So we have in total 9 data origins in 2 continents. They serve both public data like LIGO and a bunch of other things, but also private data like LIGO. LIGO's private data is available via the same infrastructure as the public data and literally just moves from namespace public to private every 18 months. And so we just, I think a few weeks ago, there was such a transition. And then I will talk more about you can, as institution or as individual, you can donate hardware into this. You can bring hardware that has data on it in order to compute in it and then access that data via the caches. And so that this is an open infrastructure that anybody with a US affiliation in the science can join. So if you have some other project you'd want to use this for, be my guest. So the big picture of what's involved here is that OSG supports a modular software stack and a fabric of services. Basically, we support a software stack that you can download and deploy yourself. And we support a set of services that we run for you so that you don't have to download the software and run it yourself. And you get to pick and choose depending on your cybersecurity stance. If you're willing to give us some kind of root access, we're happy to deploy. And I'll talk more about how that works. And the environment for multiple organizations, this gets fairly complicated very quickly because given that there is a notion that the owner determines who gets access, and given that resources might have multiple owners, the Venn diagram of actual resources and who gets to access them is arbitrarily complex. It's just, there are some groups that share resources, that they may share services, they may share data in global namespaces. The full complexity that you can imagine creating with such an infrastructure, we actually have. Everything that you can imagine does exist to some degree. And then on top of this, we're giving you all of this to make your own infrastructure. And if, in essence, LIGO, Virgo, Kagra have built their own infrastructure out of our components, but they also use the public infrastructure that is available for everybody else. And so OSG runs its own infrastructure, uses the OSG tool. OSG is both a provider of services and a consumer of services. And as a consumer, we provide all of this as a structure for anybody. If you want to do math on, if you have large mathematical models to calculate whatever, you get an account, voila, you're a customer of OSG, and you then would run on the OSG infrastructure. We support the common good by democratizing access. Not just the billion-dollar experiments should have this sort of thing. We eat our own dog food. For me personally, this is the most important reason. I believe firmly that if you're supporting something for others, you must know how to support it for yourself, because that's how you learn how painful it is to support what you provide. So you have to eat your own dog food. We teach others how to follow our lead and support their own. So it's a full service of some sort. Now, let me talk a little bit about what this environment actually is. There is sort of two pieces. There is the Compute Federation, which we call the Open Science Pool. And there is the Data Federation, which we call the Open Science Data. That has components. There is a submission infrastructure that functions as an access point. For those of you from within LIGO, it's just a Condor submission infrastructure. Basically, whatever you're familiar with by logging into Caltech resources or whatever, it's the same identical thing. You ultimately talk to a Condor SCED. Then there's a workload management system which provisions resources, creates a Condor pool that is global in scope. These hundreds of different clusters, literally, we submit a Condor infrastructure into them, a batch system into them, create a big batch system across the entire world, and voila, that's where the LIGO's jobs run in. And you can make arbitrarily complex workflow, meaning Pegasus is supported. Again, for those inside LIGO who know the tools, it's all the same tools that LIGO uses natively. We provide a homogeneous runtime environment across heterogeneous resources. It includes dozens or more types of GPUs from NVIDIA and AMD. It includes some FPGAs, and it includes hundreds of curated containers. LIGO itself has its own curated runtime environment within this context. And so you can make such requirements, like I said on the previous slide. I want to run only on compute resources that have access to the LIGO runtime environment. And voila, you have all of the libraries and so forth in an environment that LIGO is familiar with. Then in addition, there is the open science data. There is storage that functions as data entry points. I tend to call them origins of data. And then there is the global content delivery network that makes data access transparent. In essence, we run an infrastructure so that you can land anywhere in the world and have a reasonably close data cache that you can access as if it was local. It sort of creates the impression of a global read-only file system, because it literally you can read it with you can access it with stuff that is almost POSIX syntax. So just like a file system. We're supporting public and private data. And as I said earlier, any researcher in the US can request access to this environment. So you could access, if you're doing, we have actually economists, mathematicians, all kinds of people, anybody who needs large-scale computing to first order is fair game. I want to talk a little bit about the data aspects of this, because those are kind of less known and a little bit more unusual. And I'm going to show you some slides that I actually used a few months ago at our annual meeting to give you a sense of what kind of things are being done in terms of data. I like to distinguish modalities of use, meaning ways of using data, in order to differentiate and then talk about data. So I think of it as science that produces data. That means you have small input and out comes a lot of data. I think of it as science that processes data. That means large input, but small output. You calculate something on a large amount of data and out comes numbers, or much less data. And then there is a third use case in my mind, or third way of using data, and that is that you reuse the same data over and over and over. And that's sort of the classic case that LIGO is in, and that benefits from data reuse and therefore data caching. And I'll show you some examples for each of these, and I've picked them all from astrophysics or astronomy, given that there is some notion of multi-master astronomy. One of the things that this infrastructure is useful is, in principle, all astrophysical instruments, all astronomy instruments could all put their data in there and then share it across each other and share it with people like in this building, with mathematicians, statisticians, in order to work together, do stuff together. And that sort of is very natural as an example of how to use this infrastructure. So my first example is the modality 1. There's an experiment called it's a ring imaging Cherenkov technique detector. Basically, it's an array of detectors that looks for air showers. And Nepomuk Otte from Georgia Tech did large-scale simulations for that in order to improve their pointing accuracy and improve their reconstruction. And so he created a data sample of 400 terabytes on OSG and is now making that available for use in the collaboration to improve their reconstruction and therefore improve their science. Another example of the second is SPD3G. It's in a telescope at the South Pole. It does cosmic microwave background polarization measurements, and the latest version of this, the latest incarnation of it, has 12,000 detectors that are, or 12,000 channels, if you wish, that are sampled at 1500 hertz and collecting therefore terabyte a day of data, give or take. And all of that raw data then needs to be turned into maps of the sky, of the CMB, correlations, and ultimately derive polarization maps. And so this is roughly 5 to 10 million CPU hours per science paper here. So it's massive amount of, or large amount, almost LIGO scale amount of computing, but with very little output because these maps literally are very small. And the next generation CMB instruments in the late 2020s will collect about 10 times as much data. So we have very large data that needs to be processed. Out comes map. Those maps become then the public result, and then you do the science on these maps. And each one of these, I can send you the slides later, and then if somebody tells me who to, there are links embedded into the slides to presentations by these people on that kind of science. And the third one, there's about 100 projects, many of which are single PIs, basically not large collaborations, but individuals that just have data and have very heavy reuse, or in some cases not so heavy reuse. And they use the caching infrastructure. And they use the caching infrastructure in part because they heavily reuse data, in part because it's just damn simple and convenient because it hides any kind of data movement from you. Data is just there. And so it's convenient. And I've listed here, what I've done is when you think about how data is accessed, you can calculate the working set, which means the totality of unique data that has been accessed in a given period of time. Or you can calculate the total amount that data is read, and then you divide the two, and you get the reuse fraction. And so I've given you a table here of these three sets of numbers, and then I've ordered them by who has the largest working set, and then I've given you sort of some sense of who these people are, at least by name, and if I remember them, I can probably say which one's which. This one is a single individual. She's a genomics. She's actually a biostatistician doing genomics in food science. She analyzes data for tracing in food contagion and stuff like this. And then LIGO private, LIGO public. In between, you have some individuals that these two, if I remember correctly, do detector development for future instruments in physics. This here is another, she's an evolutionary biologist who studies genomics for gene evolution and tracing in evolutionary history through genes. And then, or you can do this the other way around. You can do projects with largest reuse. In other words, you take the same data, just sort it differently. And then you can see that there is the NOVA experiment, which is a neutrino experiment in particle physics. It has a very small working set, but it has a large reuse. That's most likely input data for large-scale simulations. Typically, the large reuse kind of things with small sets our input data, say, think of it as noise data that gets is used as an underlay in order to make realistic simulations. That's the typical kind of case for this. And then you have another one here. Dune is another particle physics experiment. SBND is particle physics experiment. Microburn and Minerva, those are all particle physics experiments. And then in between, you have some individuals which are forgotten who they are. But the basic message is, on average, the infrastructure served a working set of 200 some odd terabytes, and it got read 22 petabytes worth. So the average reuse is about 100 times. In fact, I have some of the range of sciences listed here. Some of the people that I didn't remember is plant genetics, computer engineering, and I think the others I mentioned. Fundamentally, you could do with this time series analysis for stock market data. That's a very classic thing that some people use to analyze over and over and over. And it's a modest size sample. It would perfectly fit into this sort of thing. So how can you join? You can join resources, data, or you can join an access point, or you can join as a user just by getting an account. Any one of these is possible. So I'm talking a little bit about how institutions that are members of LIGO or Virgo or Kagra can join their institutional resources to the global collaboration of the three, and therefore get more done together. You can join an entire cluster via something called a hosted compute entry point. You could join an individual compute node by joining a Kubernetes infrastructure. You can join a Kubernetes cluster via Admiralty. This maybe gets a little bit into the weeds of techno speak. You can also join you can send us your credit card and your Amazon account, and we will purchase for you on your account and join your rented commercial cloud infrastructure, if that's of relevance. We've done this a few times. We've had at various times customers where they got, for whatever reason, either an allocation from the NSF, or had spare cash to burn, or got an allocation, freebies from the cloud providers themselves. So we created it temporarily for a week or a month or clusters inside the cloud providers, in some cases even global clusters across the cloud providers, across all three dominant cloud providers, and merge that into the infrastructure so that it's completely transparent for the end user. And voila, science gets done. On the data resources side, you can join file systems or part of it. If you have a global file system in your institution that is 10 petabytes, that is used by many different customers, you can join just one directory structure, directory hierarchy in arbitrary complexity, essentially, or a few different directories. And I'll talk a moment about how this gets done. You can join empty storage via HTTPS to write. So we can actually use the storage that you provide. We can use your data that you come with on your storage. We can use your empty space for you to use to store output. And the output that you've stored can be reused afterwards in computation on the same infrastructure. So you can embed data and resources. What has happened a fair amount is that LIGO, in the global LIGO-Virgo collaboration, they have allocations on a variety of different clusters that we already work with for other customers. So it was easy to integrate the clusters, but it was then a pain in the neck to get the data there. And so those clusters would then donate caches, we would run them for them, and voila, the data of LIGO becomes available transparently on those resources that were joined. That's a very common thing that we've done. And then if you have your own Condor cluster and already have all of this deployed, we can integrate this and allow you to use the infrastructure that you use for your home use to also go into the global infrastructure transparently. And then the actual submission that you make, meaning the workflow that you submit, you can say these jobs are allowed to run only on my cluster because they need a license of some sort, for example, that I don't have in the world. And these jobs don't need a license, they can run anywhere. And all of this can work dynamically, and we support the infrastructure. I made this picture this morning because I didn't know who am I talking to. It's probably way too much techno speak for this audience. It basically formalizes conceptually how you share data and storage out into the world. Imagine that you have a file system. This is your file system in your institution. And this is behind the institutional firewall because you're cyber paranoid. And so what you then have to do is you have to have a dual-homed host that joins a Kubernetes cluster that one of our partners operates. And that host simply mounts whatever you want to export. So you completely control what data is visible to the outside world. And voila, we make it happen. And that's sort of the simplest way of bringing data into the infrastructure. Then what's the kind of flexibility that you have in terms of what are the things from a user perspective, researcher perspective, what can you do with this? You can export part of a file system that can be exported read-only. That's the most common use that we actually have. People have file systems, some part of it they want to export, some part of it they don't want to export because it's somebody else's that doesn't want to do this. And so you we mount the part that wants to be exported, and voila, it goes outside read-only because it's just to access and to compute on it by the caches. That's probably the most common use case. Another part you can open up for writes because maybe you're trying to produce data on the infrastructure, or you're analyzing data and there's a sufficient output that you want to bring back and you want to write this into your storage at home, or you have intermediate data products. I'm told that LIGO nowadays is starting to see more and more workflows where there is intermediate data produced that needs to be stored somewhere temporarily, and then at the end of the workflow, that data isn't needed anymore and gets deleted. That sort of thing we can also support. And the last thing, in my mind, is interesting because when you're sharing data, sometimes you produce something for the community, it's on your server, but you need the space back. So you need to move it somewhere. But you want to move it somewhere such that everybody still can use it and it hasn't disappeared. The structure of our data federation is such that that is automatically supported. Meaning, for example, you could produce data that you privately produce that is eventually valuable enough that LIGO wants to share it with everybody in the collaboration. Originally, it sits on your private server. You can then move this to a public server, meaning a collaboration-wide server at Caltech or anywhere else, for all I can in Europe on Virgo. And as long as you arrange the namespace appropriately, your private copy and the public copy will look identical to the entire user community. So once the copying, the replication is done, you can delete your private copy and use that space again for the next stuff that you do. So that way, data can migrate between being experimental, being worked on, and becoming public for the common good of the collaboration or the common good of the world. And without it having to be sitting there using up your space that you bought and own. And that kind of thing is automatically supported by the infrastructure. So next I wanted to talk a little bit about where we're going with this. So this is all the stuff that basically exists. And different science communities use different pieces of it. I don't think anybody uses everything that I talked about just now. Basically, different communities have different subsets of what I just talked about that they use according to what they need. So where are we going? The next thing that's happening is that we're actually, if you look back, at this map, the obvious question is, how on earth did we decide where to put caches? Well, haphazard. Whoever had a cache, we put it in. Basically, anywhere where somebody was willing to offer a cache, we integrated it. And now the next step is to actually go a little bit more systematic. And so I wrote a proposal a year ago, and it was funded by it was reviewed and has been awarded by the NSF, where I approached the problem very simple. I made myself the map of I went to Google Maps. I made a map of the US, and then asked myself, what's a reasonable distance for our technology to do data access? 500 miles works. Anything larger than 500 miles gets a little complicated. And then I made circles of 500 miles and did a little bit of Tetris and asked myself, what's the minimum number of circles and where do they have to be in order to span the US? Voila, that's the map. And so this project will put caches in all of the circles, at the center of all of the circles, therefore have cache access to anywhere in the country within 500 miles, and well, modular some Texas places, maybe, anywhere in the country, and places where nobody lives are excluded. And then this will get deployed next summer, and voila, that gets added in, and then we actually really have systematically a caching infrastructure that will serve any place in the country, or approximately any places in the country within 500 miles for access. This does a whole lot of other things that I'm not going to talk about in this. It provides a boatload of GPUs and some FPGAs and all kinds of other funky stuff to make it attractive as an NSF proposal. But from the perspective of this talk, the most important thing is that it makes a systematic coverage of the US with data infrastructure. During the prototyping phase, we want to be open to all. The NSF has all kinds of different ways of doing allocations these days. In fact, there's sort of 3 different types of allocations for different communities. We want to ideally serve all of them, and we'll figure out whether this is possible. There is another aspect to this, and that is that we are offering this infrastructure up just like before in such a way that people can join their own resources. And at a granularity, anything from a single host. So if you are a machine learner, so you're a computer science professor who's just bought themselves a piece of hardware with the latest gaming GPUs because they're cheap, and voila, you want to join this to this infrastructure, that's possible. We have, on PRP right now, there's about 500 and some change GPUs. 75% is contributed by individuals. And most commonly, it's a single host with 8 GPUs in them. We even give you a shopping list of what you have to buy because we've already verified that that works. And voila, you go off, spend your money, put it in your institution's science DMZs, and off we go, we operate it for you. We even do the system administration in this case. And so this kind of integration of the rationale, my long-term vision and goal is that if you look at the country for a moment, you will find that there's about 4,000 accredited institutions of higher learning, public research institutes, and national labs. There's 3,900 colleges and universities, and then there's 100, give or take, labs and national labs and other non-profit research institutions. In an ideal world, you'd want to create an infrastructure where all of them can join, and therefore anybody can share data with anybody for any purpose, research-wise. Now, if you want to do this kind of thing, that's sort of what is my vision long term. If you want to do that kind of thing, you have to deal with all kinds of scaling problems because you'd have to go from where we are today, a few hundred, by another order of magnitude up without scaling the number of people that support this by an order of magnitude. And that's sort of one of the research topics that I'm personally interested in, and where I do cyber infrastructure research in a way. And so if you then ask yourself, if you want to do this in order to democratize access to large-scale computing, then you want to reach every single small college in any place, rural or otherwise, in the US. Now, at that point, you have to be willing to do a whole lot of variety of different things. You have to be in a position where you can start by operating a single server that somebody just buys the hardware, puts it on a rack, and then a team that knows what they're doing takes over, because that small institution does not have the resources to afford a sysadmin even. And so you go from there to the national labs, which have armies of people. And you have to create infrastructure, software, services that can go from mom and pop shops to national labs and somehow get that all integrated. And that's what we do. And that's where some of my own research in cyber infrastructure goes. I talked about the innovative data infrastructure. It's built on the OSG data federation that I talked to you about, and the concept of regional Ceph clusters. Within PRP, and I didn't mention this, I should have probably, within here, there is 8 circles total. 5 are green, 3 are blue. The green ones are just caches. The blue ones actually have origins in them, meaning they have petabyte scale storage systems at the center of the blue, and they have GPU infrastructure, compute infrastructure, and so forth. So this entire project both puts a national scale data infrastructure out and computing in 3 different locations, and then it's going to be accessible for anybody and their brother and sister to join their own infrastructure to it via the Bring Your Own Resource program. We want to allow, in OSG, we have a lot of experience with Bring Your Own Resource for compute. We have a lot less experience for data, especially the notion that you have storage systems that may even be not locality bound, that may actually be distributed. In PRP, we've experimented with this. Right now, for a while, we ran a storage system that was spread across the entirety of California. It had pieces in Northern California and pieces in Southern California. That turned out to be really painful to work with because of the speed of light is finite, right? And so we are splitting it up into reasonable sized regions where you have regional Ceph storage, and then you replicate between regions. So that sort of thing. And that's where this 500-mile actually is a result of experimentation, if you wish. For the kind of applications that we typically see, 500 miles, the latency implied in 500 miles is okay for the access patterns that we see. Some project details from the NSF. The interesting bit is it is supposed to be go live somewhere around July 1st, 2022. Anybody who's bought any hardware recently knows that this is probably a pipe dream, because we actually recently, at SDC, we recently ordered switching gear. We ordered it in September, and it is going to be delivered next May. That's the kind of lead times that we right now have on some tech products. It's incredible. Conclusion and summary, we're operating an open global infrastructure that any campus and researcher can join that is affiliated with any user science program. That's actually important, given that we're funded by the NSF. I'm allowed to work with people outside the country that have research collaborators inside the country. For example, I've had requests from people in Latin America that want to join LIGO and want to join their resources to LIGO. That's fair game, because LIGO is a US-supported experiment. Similarly, if you have a collaborator in any country, almost any country in the world, there's some iffy things, then we can make that happen. So we are ultimately about global collaboration. And we have on-the-ground compute federations. These computer federations serve CPUs, GPUs, and FPGAs. They basically serve anything anybody buys to first order. And anybody who wants to bring in a piece of hardware, we rarely say no. In fact, I can't remember ever having said no, but I probably did. And then there's data federation, where you can bring in data, you can bring in storage, you can bring in caches, and we provide a content delivery network. And if you want a mental model, we're not Netflix, we're not YouTube. We're closer to YouTube than Netflix. But imagine a YouTube where you can not only upload data, but where you can also join your own hardware. That's what we are, basically. And that's it. Thank you very much.